Fortune 500 companies trust Interoptic for optical transceivers and cables. Since 2004, Interoptic has provided high-performance optics and cables at a fraction of the cost of OEM gear. Interoptic products are 100% tested and backed up by real engineers. Work with the optics experts at Interoptic. Find out more at interoptic.com/packetpushers. Welcome to Heavy Networking, the flagship show in the Packet Pushers podcasting armada. I'm First Mate Drew Conry Murray here with Captain Ethan Banks, and today we're setting sail for the murky waters of Kubernetes networking. And while Kubernetes may be more relevant to the developers in your life, a lot of networking happens under its covers. So on today's show, we've brought aboard a pilot to help steer us through some Kubernetes networking essentials. Our guest is Karim El Jamali. In his day job, he's a product manager at F5. But for today's show, he's here under his own recognizance, as this is an unsponsored episode. Karim blogs at jamali.hashnode.dev, and you may have seen some of his blogging work if you're a subscriber to our Human Infrastructure newsletter. Karim, welcome to the podcast. So I just want to level set quickly with some background on Kubernetes. My understanding is that in a container-based or microservices environment, containers are an element or a component of a broader application. And to make that application work, you need to coordinate and connect all those containers. There are different ways to do this, but Kubernetes has kind of emerged as a popular orchestration platform. Did I miss anything there?
Drew, you're spot on. Containerization is generally about packaging software functions, right? So think about like an application where there are multiple components. Authentication could be one of them. Checkout could be another one. Mm-hmm. This is part of an overall service or application that a corporation is delivering. Kubernetes is an open source platform for managing all of these containers and services at scale, tackling topics like high availability, scheduling, networking, and security.
Yeah, so let's kind of build a mental model. What are the key constructs I need to be thinking of when I am thinking about a Kubernetes environment? What are the core components?
So let's start with the container. The container is, again, it's basically a package of code and all its dependencies. The whole objective of it is to make an application or a component portable across users and environments. Now, a container does not exist within Kubernetes, really. A pod is the smallest unit of compute in Kubernetes. So what's the relationship between a pod and a container? A pod can have one or more containers. And you can think about the notion of a sidecar. Some examples could be that you have two containers running in a pod. One container could be downloading images, and the other could be, for example, changing the resolution of these images. Another possible example is generally logging. You can have a container that spits out logs in a particular format, and another sidecar container sitting in the same pod that changes the structure of those logs for a particular purpose. Service mesh, which we will get into later, is also a third notion of the use of sidecars. And again, sidecars, if I didn't make that clear, is about running containers, one or more containers in the same pod.
Okay, so we've got containers, which is the code. We've got pods, which is the unit of compute that a single container or multiple containers can live in. I presume we also need some kind of resource to run these pods on.
You're exactly right. Again, node is basically just a physical or virtual compute resource on which these pods will run. And nodes generally function as part of a Kubernetes cluster, which is the grouping of nodes as well as all the control plane and all the Kubernetes magic that makes all of these nodes function as a single entity.
Okay, so pods contain my containers. Pods run on nodes, which is the compute. It could be bare metal, it could be a VM or something else. A node is, I think, of compute. And then if I've got a bunch of nodes, that counts as a Kubernetes cluster.
Exactly. And just a point to add, like if you see some of the cloud providers, AWS, Azure, they're also trying to get this complexity away, that you don't have to manage the clusters, the nodes. So what they're doing is they're offering managed Kubernetes, where you just say, I want to deploy these pods, I have these apps, and they take care of the infrastructure, of the upgrades, of all of the operations of managing a Kubernetes cluster.
And when we get into Kubernetes networking, there's a notion of a CNI, a container network interface, that I've read a lot about. It's an API, it exposes stuff. There's different providers that plug into this thing. Can you tell us what the CNI is all about?
Yeah, so Kubernetes naturally does not have a networking implementation. So CNI is a way to plug in diverse networking implementations into Kubernetes. So the idea is, the way it works is there is on every node, there is a function called a kubelet. Okay, so think about the kubelet as like the owner of the node. And there is the master, which is the Kubernetes brains. So whenever we say that we want to create a pod, what's going to happen is the master is going to inform the kubelet that you want to spin up a pod. At this moment, the kubelet will go and call the CNI, which is our networking implementation of choice, be it a Cilium, be it a Tigera, to go and do the network stitching, which involves, I want to run a cable, which we call it a virtual Ethernet cable, to that pod. I want to give it an IP address. I want to do the necessary routes to get this pod up and running from a networking perspective.
Do I have networking without the CNI, or is the CNI, I mean, it's not exactly my gateway to the rest of the world, but it's a plugin to give me additional networking functionality?
No, so Kubernetes, you will always have to use a CNI for Kubernetes. And,
Okay.
and CNI has nothing to do with the outside world. Think about CNI. I mean, it could have, but CNI's basic goal is to get these pods across all of these nodes connected to one another.
Okay. So that is all internal communications.
Yes.
The pods on nodes talking to one another is a networking challenge all on its own.
Exactly. Because, I mean, you have to set up a network inside. Basically, all of these pods on a common node will have to run within a common network. And then you have to decide, how will one node communicate to another node? Do you need overlays? Are you going to go native? Topics like VXLAN, Geneve, and all the networking topics come into play. So Kubernetes does not run without a CNI. You always have to invoke a CNI. And that CNI is what does the networking plumbing and get all of the pods connected to one another.
Yeah, in some ways, I think this is part of the genius of Kubernetes. Like, they knew they needed to connect all these containers, but they're like, that's not our specialty. Let's let a networking specialist handle that. So that's why they made this plugin format. Is that correct?
Exactly. And you see it like repeated across different like storage and different technologies within Kubernetes, because Kubernetes is really a very wide technology that touches many different things.
All right, so let's get into some networking basics. We've got the notion of a CNI, and if we're thinking sort of, we're talking about inside a cluster at this moment. So how do containers within the same pod communicate? So I've got, 2 or 3 containers in one pod. How do they talk to each other?
So it's basically like processes on a common host or a common VM where you'll use like a local host communication. So basically, remember, like we always have the 127.0.0.1 address that refers to localhost. And basically, one process will be calling the other process by just the port that this process runs on.
So they're basically in the same. They live next to each other. They're
Exactly.
neighbors. They can see each other. There's not a lot of fancy magic going on there at all.
Exactly. I mean, basically, if you look into it, they call this as a network namespace. So they're basically in the same. Yeah, they have the same routing table. They're in the same networking view. So all what you need to communicate between processes is the different ports they run on.
Okay, so we've got a sense for how containers within the same pod can talk to one another. What if I've got pods on the same node? How do they connect and communicate?
Yeah, so again, it's interesting to mention is like there is a virtual Ethernet pair. It's basically like a virtual cable that connects the network, that connects the pod to the host. And you can think about all of these pods as being plugged into a common network on the host. So basically, communication goes like layer 2 communication on a VLAN within pure networking.
Now, the issue would be the pods are in different network namespaces. So by default, they can't talk to one another, even though they're on the same host. And so we've got to do this virtual Ethernet pair plumbing to facilitate that connectivity.
Exactly. Without the virtual Ethernet pair, that pod is isolated from everything in the world. The virtual Ethernet pair is what gets the connectivity from the pod namespace to the host namespace or to the root namespace where all of these pods are plugging in.
So we're not plumbing pods into each other. We're plumbing pods into the root namespace, kind of like a hub and spoke.
Exactly.
Okay.
And is it the CNI that's essentially setting up this plumbing for us, giving me these constructs?
Exactly. Whenever you spin up a pod, it's the CNI's job to get this virtual Ethernet up to the host and providing an IP address to that pod, as well as doing other things with routing.
Okay. All right. So we've got container to container communication. We've got pod to pod communication. What about pods on different nodes? Different forms of compute. How do they connect with each other?
Okay, so this is a bit more interesting and complex. Now, since we've looked at pod-to-pod communication within the same node, the difference here is once you reach the host, there are a few networking decisions that have to be made, which means how are you going to connect your nodes together? Are you going to use an overlay? And this is where topics like VXLAN, IPsec, Geneve, and WireGuard become a topic. Or do you want to do native, which means do you want to when the traffic gets out of the node, do you want to keep the pod IP addresses? And this would also mean that your underlying network would have to know how to route the traffic between the pods. And this is generally a networking architecture decision on how you want to run your pod-to-pod networking across nodes.
Because those pods may not have addressing that the network engineering team even knows anything about necessarily. Is that the point you're making?
Exactly, because generally when people run Kubernetes, it's usually developers and they choose a pod sider, and that pod sider could be overlapping, could be used somewhere else. And generally the easiest way around it is to use an overlay, because then your underlying network will never see that.
You tunnel. All you have to care about from a network engineering perspective over that the public network, if you will, that the nodes are connecting to is endpoints. You need to be able to get endpoints to be able to talk to each other, and that's it. You can push anything through the tunnel you want.
You're spot on.
Now, you mentioned VXLAN, IPsec, Geneve, WireGuard. Is there a preferred or typical way that the tunneling encapsulation is done, assuming that that's what's chosen?
I see VXLAN a lot across many of the vendors. Generally, some requirements do mandate encryption, and this is where IPsec generally rules. WireGuard is another alternative that has been lately introduced. As far as I'm aware, it's not yet NSA certified. So
yeah, WireGuard's an interesting one. Just I didn't know about the NSA concern as far as that goes and what its encryption levels are. I assume that's what the discussion is, but it is lightweight, friendly, and programmatically accessible if you want to stand up a WireGuard tunnel, as I understand it. And I've seen it pick up favor in a number of VPN solutions for that. So it's interesting to see it show up here as a possible Kubernetes node-to-node connectivity transport.
Yeah, exactly.
Let's pause for a message from our sponsor, Interoptic. Interoptic is the optical transceiver and cable specialist that maximizes your IT savings while minimizing network failures. Interoptic provides high-performing optics at a fraction of the price of brand-name optics. The Interoptic experts can help you spec the best optical transceivers and cables for your network environment. Interoptic optical transceivers are 100% guaranteed to be operationally equivalent with Cisco, Juniper, Extreme, Arista, Brocade, Palo Alto, and many other switches and routers. Due to Interoptic's deep optical transceiver technical experience, they can ensure that all messages, alerts, alarms, and threshold data are equivalent to OEM brands. Interoptic deploys rigorous 100% testing on their devices before they're shipped. Interoptic optical transceivers are built to the exact same quality standards as the OEMs and typically come from the exact same manufacturing lines. That's why insurance companies, retailers, financial services, and federal and state government customers deploy optics and cables from Interoptic. You can purchase the same, if not better performing optical transceivers, tested and backed up by real engineers at a fraction of OEM costs. Find out more at interoptic.com/packetpushers. That's interoptic.com/packetpushers. And now back to the podcast. Okay, so we covered some basics about networking within a Kubernetes cluster. I'm curious about how IP addressing is handled within all of these pods and clusters, especially considering the fact that containers are typically intended to be ephemeral, meaning that they can spin up, they can spin down as needed, so they might not be there. So how do I get IPs to all these devices?
Got it. That's an interesting question. Again, this is a difference from how the HCP and regular IP addressing works, in the sense that what happens is when you start a Kubernetes cluster, you say, I want to have a pod sider, which is basically the IP block that I will use for this Kubernetes cluster to be, for example, 10.1/16. And one of the implementations that is a common one. So if you have 5 nodes or 10 nodes, that super block gets subdivided into equal blocks across the different nodes. So just to make it simpler, let's assume each node takes a /24 block. And now whenever a pod is scheduled on that node, what happens is the kubelet again calls the CNI, and one of the roles of the CNI is to give that pod an address from the block that is associated with the node. There are other implementations, but that is generally a common one.
Kubelet calling CNI, that's different from DHCP, or it feels different from DHCP. It feels like an API call.
Yeah, it's exactly. That's where the difference. There is no logic of ARPing and broadcast and DHCP server in that sense, because the pod is a programmatic thing. There is an API call to create a pod. The kubelet is going to tell the CNI, give me an IP, and this is how the IP will be provided to the pod. So it's more of a programmatic API thing rather than DHCP requests and broadcasts and all of that stuff.
So where does this initial CIDR block come from then? I feel like we're getting into chicken and egg questions. Like, I don't know which comes first.
Yeah. So whenever you start setting up a Kubernetes cluster, you will have, there's a default one, but generally you will have to go and set up your pod CIDR. And that's the only thing you set. And then the system is intelligent enough to subdivide the pod CIDR into multiple blocks and give each node a sub block of that. This is one implementation. There are other implementations that are a bit more advanced.
Okay. Now, if I'm setting it up on-prem, I assume I've got to assign a CIDR. If I'm doing it in a cloud using a Kubernetes service, does it provide a CIDR for me, or do I also choose that?
You can also choose your pod CIDR.
Okay. So we're getting pods and nodes and everything to talk to one another. Can I, if I need to, make sure that there are pods that I don't want to communicate with each other? Can I do that as well?
Yeah, that's again a very important topic whenever you talk about networking and security, which is the concept of Kubernetes network policies. One idea I think I need to make clear is by default, in Kubernetes, every pod can communicate to every other pod. Obviously, if they're set up correctly and everything is functioning.
Every pod can communicate to every other pod on a node or even across nodes in a cluster?
On a node and across nodes.
Wow, okay.
Okay. There is no logic of a VRF or different routing tables or different routing domains, which makes the need for network policies a very important need. So think about network policies as like a firewall within your network. And it's, again, what's nice about all of this is it's all a config that you give to the API, and Kubernetes goes and applies these policies via the CNI. It's not a Kubernetes native implementation here.
Okay.
The other thing that's very important is because what we mentioned, because pods are ephemeral and because there's a lot of incoming pods and pods that come and pods that leave, labels are a very important value here. So generally people, when they're writing policies for Kubernetes, we don't write policies from IP to IP. You generally label your pods. And this becomes much easier when you want to touch a ton of pods that you don't want to talk to other sets of pods. So the labels become like the tagging criteria. So it's basically you label a pod, and then whenever you're writing a policy, you're doing a selector. So that selector means go in all of these pods. This policy will apply to all of the pods that have that particular label.
Okay, so you're saying I shouldn't be making my connection policies based on IP addresses because those IP addresses could change because we're in an ephemeral environment. I've got to use labels instead.
You're exactly right.
Can you give me an example of a label? Like what kind of a label would I use? Yeah,
so just a very easy one. Let's say you have two environments, dev and prod. Again, because there's no VRFs, there's no routing, they all can talk to each other. So at a minimum, I will label my pods. One of the labels I could use on my pods could be environment dev. And the other ones could be prod, and I can write a rule, dev does not talk to prod.
Okay.
That could be an Uber rule, right? Yep. You can think about this as a very high level rule, and then you can get into your apps and start doing sort of a zero trust policy so that you close all, you basically lock down your environment to the required ports and communications.
Okay, so I could be rolling out sort of like a set of nested labels to actually build out my policies.
You're exactly right.
How do I find things within my Kubernetes cluster? How does a pod find another pod it needs to talk to?
Again, because pods are ephemeral in nature, we bring up the concept of a Kubernetes service. Think about a Kubernetes service as an IP address, a virtual IP address, whose IP is always fixed, okay? And that has a DNS name, okay? So, and behind this service is the pods are the pods that you want to reach. It could be one pod, it could be 10 pods. So this becomes interesting because no matter how many pods you bring up or you remove, as long as I'm talking to that service and that service has a functional pod behind it, this communication will work. The other important aspect to mention here is, how do we find the service? Whenever you create a service, a DNS, there is a functionality in Kubernetes, which is a DNS. And that DNS, whenever you create a service, there will be a DNS entry for that service. So this becomes very easy. Let's say I create a service called foo. So in a namespace called default, it will automatically have a name foo.default.something. Mm-hmm. And anybody who would want to communicate with that service, it will automatically resolve and you will get to one of the backing pods.
It resolves to the virtual IP, and the virtual IP is going to pass my request through to a pod. Some pod, it's an ephemeral pod. It's going to be there to service the request. So it feels like the way a load balancer service functions, at least on an initial level. There's a virtual IP and typically pool members that sit behind that virtual IP on a load balancer. This feels like similar to that, but maybe less. Maybe there's not persistence or sticky sessions or something. It's just passing it through to something that can handle the request and then it's over. And so correct. Where is that? Where are we similar and where are we different from a traditional load balancer service a lot of folks might be familiar with?
I think this is the best analogy you gave. I do really think that services are in a very much similar pattern, work in a very much similar pattern to load balancer. There could be some intricacies like the one you mentioned, like sticky sessions thing. If you go a bit deeper into load balancers, obviously it doesn't do SSL termination and all of that stuff. But from its idea that there is a VIP and I want to give it to pods or resources that are behind that VIP, this is very similar to a load balancer.
So another point of distinction here then, is the virtual IP acting like a proxy, like a load balancer tends to, where there's a session on the front and a session on the back end, it's a true proxy. So Kubernetes, that virtual IP that presents that service on the front end is also a proxy?
You're again talking about the Kubernetes, again, like pod to pod with the service?
Yeah. Yes.
It's not a real proxy. It's more of a DNAT, NAT play. Like whenever the packet goes to the service, you will give it back to one of the pods. It does not terminate the session and start a new session.
So it's some kind of a stateful NAT. Okay, but the NAT can translate to whatever pod it needs to translate to at a given time. So you could have it DNATing to a bunch of different services depending on which request comes through. But that is an important distinction, that it's a pass through with a NAT, not a proxy, because those are just really different mechanisms.
It is. And just to go a bit behind the scenes, what this is, in the Linux kernel, there is a functionality called IP tables, which is more like they're used for firewall rules. They have some NAT functionality. And what is happening is whenever you're configuring a service, these IP tables are being programmed for you so that whenever you hit the service IP, the DNAT will happen to one of the backing pods. So it's not a proxy per se. It's more of a NAT functionality that happens within IP tables.
And then the whole point of this services mechanism is that different nodes and pods don't need to know the IPs of individual services like containers, because I can just say, I need I have to do a database lookup. So I go find the database service, and then that Kubernetes NAT function just puts me to whatever the database lookup container is.
You're exactly right. Okay. You don't need to know anything on the pods. You just know services, and services are DNS names. So it just becomes easier. The whole process flows in a much easier.
Are there multiple types of services in a Kubernetes environment?
So generally within a cluster, there is something called within a cluster. Yeah. Basically you're talking pod to pod, east-west sort of. Mm-hmm. There is what we call a cluster IP service. Again, this IP, the main difference is that this IP is not reachable from outside the Kubernetes cluster.
Got it. Uh-huh.
Okay, so this becomes like an internal load balancer that is not exposed to the external world. Any pod, and the interesting thing about Kubernetes is, remember, there could be hundreds of nodes. So that VIP is being instantiated across all of the nodes in the cluster. So whenever you hit, there is a VIP on your node, on your local node, no matter where you go. So whenever you hit that local node, that is the VIP that has the rules that's going to give the packet to one of the backing pods.
Interesting.
So it's like an Anycast VIP.
Yeah, I was just thinking it's kind of like Anycast. Yeah, kind of, sort of. Yeah. You also mentioned DNS along the way, that the service mapping, that host name service, well, the service name, I won't call it host name, but a service name is mapped to the virtual IP address via DNS. Does that mean I have to have a DNS infrastructure ready for my Kubernetes cluster, or does Kubernetes come with its own DNS?
Yeah, Kubernetes does come with its own DNS implementations. There's a core DNS pod that is running inside Kubernetes. Funny enough, it also exposes a service. So even the way Kubernetes works is the way you reach DNS is via a Kubernetes service.
Okay, so there's a Kubernetes service front-ending the DNS itself.
Exactly, and there is two pods that are running for redundancy.
Hurdles so all the way down here. That's what I think.
Exactly.
Now, you said that core DNS comes with Kubernetes, or do you mean the CNI or actually with the Kubernetes implementation itself?
No. The core DNS is part of what comes with Kubernetes. Okay. It has nothing to do with the CNI implementation.
Got it. Okay, so that was all about, sort of internal communication inside a Kubernetes cluster. I guess to just make a very broad comparison here, I'm going to think about that as the LAN. So now we need to move outside. If I want to get access externally to services inside a Kubernetes cluster, this is, I guess, where we bring in the notion of an ingress and an ingress controller. Can you tell us about the role of ingress in getting communications into and out of my Kubernetes cluster?
Yeah, I think just as a side note, ingress is not the only way to get, to get external communication into the Kubernetes cluster. There is the concept of a node port and a load balancer. I'll just touch very quickly on these, and then we'll hit ingress if that's okay. So a node port is, again, think about in a very simple terms. If you're basically doing a DNAT translation, this time from the node, right? You have a node and that node is externally reachable by other hosts. Mm-hmm. So all what you're doing is you're doing a DNAT from a port on your node to that pod internally.
Okay, so my node is my compute instance, my host. I can set up essentially DNAT so that host can communicate with the outside world to pods on my host.
Exactly. So the node, your node eventually becomes like the VIP in a sense, and I will hit the node, and that node will obviously on a certain port, and then a DNAT translation will take us back to one of these backing pods.
Got it. Okay.
This is not something we generally do in production because, again, it's not the best of implementations. Plus, you need to remember the ports. But again, this is something that works. The other iteration of this is very similar to what I've talked about, but we call it a load balancer service. So the whole idea, if you're running, let's say, in AWS, and you create a load balancer service, what's going to happen is the node port will happen. So whatever I mentioned on the node, the translation will happen, but we will bring up an external load balancer, a load balancer that is outside the cluster, that is reachable from everywhere. And this becomes your point of entry into the cluster. So in a nutshell, what happens is you hit the load balancer gives it to the nodes do the translation and give them to the pods.
Okay, so that's another option instead of running an ingress controller.
Exactly. These are like two options. Now, the downside of a load balancer, and I think this is important because this explains why ingress is there. The problem of a load balancer is every time you create a load balancer service, the implementation generally does is we create an external load balancer for you. So think about if you want to expose 10 services, you have 10 load balancers externally, and these 10 load balancers have different IP addresses, and you obviously have to pay for all of this infrastructure and public IPs and management.
Got it. Okay.
So this is the problem that Ingress is solving. What Ingress is doing is basically having a proxy front-ending all your applications within the cluster. And then you only have to expose that proxy. That proxy, just to make sure I'm clear, you can think about this like an Nginx proxy, a pod that lives within your Kubernetes cluster. And this is the gateway to all of your other applications. And then in order to expose that pod externally, again, we use a load balancer service, but we use it only for that particular service. And the Nginx is intelligent enough to do sort of layer 7 routing. So for example, if I'm going to a.packetpushers.com, I will go to service A. If I'm going to b.packetpushers.com, I will go to service B.
Okay, so my ingress is another pod, but it's inside my Kubernetes cluster, but I can configure it so that I can accept communications from outside the cluster, and it proxies those connections for me. And does it also act like a load balancer, or what is it doing?
Yes, it definitely has the load balancer capabilities. It has the ability to do layer 7 routing. I mean, it's a real proxy implementation with lots of capabilities. And the advantage I've gained here is a single entry point to my cluster. And this Nginx doing its magic and getting the packet to all of the applications that need to be exposed. The other advantage is if I were to implement security to secure this infrastructure from WAF, from DDoS, I only have that single entry point to secure versus like the load balancer service, which could be like hundreds and tens of entry points to your Kubernetes cluster.
Okay, so yeah, what other functions then can I get with my ingress controller? It sounds like I can do TLS termination, and you mentioned WAP functionality.
Yeah, so obviously TLS termination can be done, and then some of the ingress controllers do offer WAP functionality, meaning WAF, DDoS, botnet protection, and all that stuff.
Okay. How about authentication capabilities?
Some ingress controllers do support authentication capabilities. So the idea is if you're coming into your application, before you get there, we will redirect you to maybe to an Okta or to any OIDC vendor, basically, where you will go and authenticate. And once you're done, you can get into your app. That's also possible. Yeah.
Is my ingress controller separate from my CNI? Do I get an ingress controller if I use a CNI plugin, or how does that all work?
Generally, they are distinct. Ingress controllers are generally mostly load balancer vendors for the most part. Like you can think Nginx, you can think Kong, you can think other players in the industry. And what is interesting also about that ingress controller is you can manage it via Kubernetes. And this is what I think what is also fascinating about Kubernetes. You're not going into the ingress controller and going into a web UI and trying to configure it. Kubernetes is extensible in such a way that they've created objects so that whenever you configure these, you want to say, I want to configure this ingress, it can automatically get translated into a configuration for Nginx. So there is no need to like log into these appliances and manage them because, as you know, because Kubernetes is very dynamic, you could be bringing up services on a daily basis. So that is another integration point on how they can automatically configure the ingress controllers, be it an Nginx or a Kong or an F5 via the Kubernetes configuration.
Okay, so you're saying I wouldn't have to go into an Nginx UI to configure it if I'm using it as an ingress controller in a Kubernetes cluster. I could do it through my Kubernetes interface.
Exactly. Huh. And what they do, if that's interesting, what they do is they spin up. I mean, that's again another notion of a sidecar. Whenever you bring up an Nginx controller, they have two pods. They have two containers. One of the containers basically its goal is to read the configuration from Kubernetes and translate it to the other controller who basically understands Nginx.
Okay.
I mean, that's how it works.
Okay, interesting.
So is there a classic way I would be positioning, like think about this as a network architect, where would I put my Kubernetes cluster thinking about my network as a whole? Do I put it, because I bring in a lot of load balancer clusters and it feels like this is a part of it. I got to stick a load balancer in for a lot of ingress in front of my Kubernetes cluster. So how do I position it? It used to be I was sticking pool members behind it, at least logically speaking, I was sticking pool members behind the load balancer. The load balancer was in the middle. Or is it kind of that architecture, or should I be thinking about clusters differently?
So generally, if you're following the ingress model, you will obviously have to stick up a load balancer in front of your Kubernetes cluster, but that load balancer's function is just get to the ingress nginx or proxy that is inside the cluster, and that internal one is the one that takes you to all of your applications.
But I still want the users that are consuming those services coming to the cluster from the outside to probably hit that load balancer first.
Yes.
Yeah. Okay. So, I mean, that's a typical production architecture? I don't have a standalone Kubernetes cluster sitting there with services people are hitting. They're probably hitting a load balancer first that's talking to an ingress controller sitting inside the cluster, and then eventually hitting a pod ultimately from there.
That is generally the recommended practice, because again, it guarantees a single entry point into your cluster. It helps you consolidate all of your security there. And the other problem is, because Kubernetes is very easy to configure, if you leave it to people to go and configure load balancer services and everybody does his own thing, you will have hundreds of entry points to your Kubernetes cluster, and it will be really hard to manage that whole thing.
But I guess my idealistic network architecture mind goes, I don't want a single load balancer, even if it's a cluster of load balancers sitting in front of my Kubernetes cluster, because that's a SPOF of its own, and I got to think about network design requirements around that. It makes me anxious. And isn't the whole point of Kubernetes to have all this redundancy, and it spins up things when I need more of them, and when services die, it fixes them for me and all that. Now I got the stupid load balancer sitting in front of the thing. Unless the load balancer runs Kubernetes itself.
You're getting it. The answer in Kubernetes is always more Kubernetes.
And I think back to this point, this is generally the theme, but there are always ways. There is a concept in Kubernetes called a namespace, which you can think about it like from a networking perspective, like an entity or a tenant, and you can have multiples of ingress for each of these tenants and scale things accordingly. So, there are different ways to do this. The other aspect which we didn't discuss, which is possible recently, is the idea is I treat Kubernetes as part of my network. So I run BGP with my top of rack switches, and everybody knows about me and I know about everyone. This is, again, a possible model. Obviously, you need to think about the address space you put in Kubernetes. And this becomes a part of your network in the real sense. The question is obviously you need to also worry about how you're going to secure it and the whole thing. But this is, again, another possibility to do today.
Okay, so we're talking about ingress, and I guess the industry is sort of now seeing ingress evolve into something called the Gateway API. What's happening there?
So ingress and Gateway API, I think, just to first and foremost, they are eventually doing the same thing, right? It's still the same target. I want to have a proxy that is exposed externally. That is the point of entry. All of that stays the same. Where Gateway API is a bit different is it's a more role-based API. And this is a bit, if you look at an ingress configuration, it's like a monolith. So you define your ingress, you put whatever you want to route to. It's all like a single file. And this is a problem that Gateway API targets because it's very role-based. So in Gateway API, there is sort of the guy that says, I want to run an nginx implementation. And there is a guy who will implement that gateway. We call it an nginx gateway. And then there is the concept of a route. A route means I want to publish a particular domain, which is my app. I'm an application developer. So I say, I want to put a route. And this is the domain that we are targeting, and please send this traffic to these pods. So the interesting thing about Gateway API is it differentiates these three layers, and there is a back reference between each one and the other layer. So in that sense, it's very much an optimal implementation versus an ingress, which is a single file. The other value of the Gateway API is it becomes very easy to swap one vendor with another, because you're writing the exact same spec and functionality. And now if you want to replace, for example, you're not happy with your proxy, you could go and replace it with another proxy without making any changes to your configuration, or let's say with minimal changes to your configuration. Okay. Yeah. I think a third point to mention, because when people hear about this, ingress is here to stay. I think there is thousands and thousands of clusters that are running ingress, so there is no like an end of life in any sense. It's just a newer implementation, and I think customers who have invested a lot in ingress it's not an easy thing to move out. So yeah, I see them living together for quite a while.
Well, Karim, I almost hesitate to bring this up because we're this deep into the show, and we have yet to talk about service meshes and eBPF and what's happening with the Cilium project and so on. There's a whole lot for us to talk about here because it affects the networking immensely. But let's pick a topic. Let's start with eBPF. You want to talk about what eBPF is and the use cases that the Kubernetes world has found for it?
Yeah. I think eBPF is a very, very interesting technology. I think it's a game changer, really. In a nutshell, again, I'm not too much deep into the kernel and how it works, but in a nutshell, it's like you're able to run a program in the kernel, right? And I'll be very basic, but again, this is my understanding of how things work. Whenever you're running any program, any application, okay, you're running in user space. And let's say my application, my Python script wants to open a file. Okay, something very, very basic. There is a system call. There is what is called a syscall that goes to the kernel. And the kernel is the one that has to deal with the storage, with the file, with the saving. So being able to run a program in the kernel basically means the ability to see everything that gets to the kernel. Be it a file open, be it any operation, being a network packet, and the ability to manipulate all of this in code is just amazing.
Yeah. So the first time I heard about eBPF, I was like, isn't that a rootkit? Because rootkits are bad.
Exactly. So I mean, I think the power is just amazing. And one, to your point, I think one interesting point to mention, again, with my lack of knowledge in the kernel, but I know that every program you run, they have a very strict verifier. And that verifier is it either allows the program or does not allow the program. But you can think now about how much more visibility and eBPF will have. They will have a lot of use cases in security. And obviously in Kubernetes, because now every packet that comes from a pod, it gets into the kernel, and you just have immense capabilities to do things. Facebook, I believe now, last I heard, they have their DDoS implementation on eBPF. Load balancers are being done with eBPF. There is also some tie-in with some network hardware to go and try to execute these eBPF programs as close to the network interface as possible.
Yeah, so my understanding of eBPF is that it allows you to run these ad hoc programs at the kernel level without having to make that program sort of officially blessed as part of the official kernel. So it's essentially ad hoc programs, yes?
Exactly.
Yeah, I don't have to wait for Linus to update the kernel to run my application. I can run it whenever I want.
But Karim, going back to what you said, though, it's very tightly scoped. It's pretty limited what you can do with eBPF. And as you said, there's a verifier that it's not like you can just put anything you want in an eBPF program and it's like a rootkit, as Drew was saying before. It is, again, really limited what you can do. There's a lot of power there, but it's not like this is now a hacker tool. That's not the way to think about it.
I'm really not an expert on what runs and what is allowed and how does this verifier work. But from what I am seeing is I do see eBPF as companies will be founded on eBPF. I do see this, and the capabilities are just immense, from DDoS, from load balancers, from manipulating packets, from looking at security. So, for example, Cilium has a product called Tetragon that fully relies on eBPF to tell you if any pod does anything that is out of norm, just because they can see all of the system calls that get into the kernel, and you can now have immense logic on what you want to allow and what you don't want to allow. The other thing is logic of profiling of pods. So meaning, let's say I have pods, right? And I want to sort of restrict what system calls are they allowed to do. So there is the logic of I profile that pod, I see the system calls, and I know these are accepted. So now I sort of put a bubble around that pod and only allow it to do these system calls. So there's a lot of capabilities that eBPF brings into the picture. Could it be a hacker tool or not? I'm really not sure. But I think everything, I mean, it's just immense.
So let's back up for a second, because you mentioned Cilium. Cilium is a container network interface, which we had been talking about earlier. But I think one of the key differentiators of Cilium is that it is leveraging eBPF where other CNIs are not.
Yeah, I think Cilium is very much vested into eBPF. There are some other providers, for example, Tigera, that does eBPF and does other modes as well. But I think Cilium has been very much pushing eBPF. And obviously, for Kubernetes networking, one of the advantages is to get rid of IP tables, because if you ever try to look at these IP tables, they're very hard to debug. It's a technology that is 30 years old. The other thing is that whenever you go big, it tends to be slow, because it's like you have to go through a chain of different tables. And generally, this is where eBPF has a performance advantage. Yeah. One thing I didn't mention also about eBPF, which is interesting, the TCP dump tool that we use is coming from the Berkeley packet filter, which used to be called BPPF, and eBPF is just an addition on that functionality. But now they're able to, extract much more use cases, and by hooking into different hook points into the kernel.
Now you mentioned Cilium as a provider that uses eBPF heavily. Are there other providers like that, alternatives to Cilium, that people might be interested in?
Yeah, I mean, Cilium is heavily vested into eBPF. Another alternative that I'm aware of is Project Calico, which is the company's name is Tigera, if anybody is looking at this. Actually, even Cilium is the name. I mean, it's good to differentiate that Cilium is the name of the open source project, whereas Isovalent is the name of the company that is behind that effort.
Now a Cisco company, I do believe.
It is
indeed. Yeah, you're right.
Yep. Okay.
I think it's a very smart acquisition. Let's see how it goes.
Yeah. Okay, so that's a little bit on eBPF. I think let's also see if we can briefly get through the concept of the service mesh, which is taking the notion of ingress and allowing you to do more with it.
I think service mesh is a bit different. The way I look at service mesh is it's a ton of sidecar. I mean, I think let's if we go back a little, and I think it's important to mention where the service mesh come from. Why do we need a service mesh, right? Mm-hmm. There are different, before service mesh came into existence, all of these big companies, Netflix, Facebook, they all wanted to ask a common question. For example, I have an application written in Go. You have one in Python. How do we do encryption? How do we do TLS? How are we going to get monitoring and visibility? How are we going to do tracing? So they used to have a library in each language that they will get into their application so that they are able to answer these questions. So what a service mesh is coming from that background where you need to know at an application layer, you want to have observability, such as tracing. What I mean by this, okay, tracing in a nutshell is if I'm a bank, okay, and I'm doing a transaction and something goes wrong, the bank should be able to tell what happened to Karim's transaction.
Mm-hmm.
It should be able to trace it across all of its systems to know what went wrong. Okay, this is one of the major capabilities, for example, that these libraries used to bring, which were called, by the way, for reference, Hystrix or Stubby. You can Google those up. And this is one of the functionality that a service mesh brings. It also brings encryption. Okay, so you can get encryption and you can get authentication. So now every component of your software has to authenticate with every other component, sort of what is called MTLS, mutual TLS. And that is based on certificates. So think about it in a very simple terms. I mean, we could be both citizens of a common country. You show me your ID, I show you my ID, and this is how we have a trust relationship. This is MTLS.
And when you're talking about encryption, are you talking about, I assume we're getting encryption, sort of out from outside the cluster to, my cluster border, but am I also able to do encryption within my cluster, say from node to node or pod to pod?
Oh yeah, the encryption here I'm referencing with service mesh is basically a pod to pod encryption.
Okay.
Does a service mesh face the outside at all, or would I still be using an ingress controller or my own load balancer or something like that? There's a service mesh. If you see what the distinction I'm trying to draw here, we've talked on this podcast about the internal communications, node to node and pod to pod, and then having something separate happen so that I can speak outside of the Kubernetes cluster to something else. Where does a service mesh fit in? Is it just for that internal communications, or is it also for external, where maybe I, as a consumer of a service, am hitting an IP that lives on a service mesh somewhere?
So the service mesh has both. So the service mesh is mostly about east-west between my pods. Okay. And again, the idea here is not networking in its connectivity sense. It's more about give me the observability, give me the authentication, give me the encryption, give me all of that additional functionalities. But Ingress, for example, can also work with Gateway API. That was the previous topic. Yeah. And this is how you can get traffic into your Kubernetes cluster.
Okay. So I don't want to have to, as a coder writing an application, bake encryption or observability or whatever into my app. I want to offload that functionality to a sidecar proxy that's going to handle that for me and kind of catch the traffic on the way through, provide that functionality as that traffic flows through it.
That is exactly what service mesh is all about. Another very good use case is how do you know how your application, for example, if I put a latency of 10 seconds into a certain component, how will your application operate? All
Slowly.
Of these questions. Exactly. That's a good one. So the idea here is that these proxies can get all of that. So it's not really about Kubernetes networking. It's about looking at an app-centric view of the world. Encryption, authentication, inducing errors, inducing delays, being able to do more tests. If you release a new release like a canary release, how are you going to do blue-green deployments? All of that stuff is what a service mesh really brings into the picture.
Okay, so the reason a networking team might be interested in understanding service mesh is because they can get some performance metrics and so on, where if someone's saying the application is slow, and it's the network's fault, they can go and actually look.
Yes, and I think most of the time, generally, if you want to talk about service meshes, it's generally the app teams and the platform teams that will be very much concerned. Okay. Because when the application performance team is going to say, my app is not doing well, you want to be able to show him the traces, you want to show him the visibility and the monitoring and all those capabilities. So it's mostly, it's not a networking technology. It is more at a bit of a higher level.
Yeah, that just hit me. It's really higher up the stack. It's Yeah, it's plumbing on these additional features at an app level, and not yes, networking traffic passes through it, but it's not a networking construct as such.
Exactly. And I think if just, I mean, as a side note, the way it happens is, remember the sidecar discussion we had where you put two containers in the same pod?
Hmm.
What they do is they put an Envoy proxy or a proxy basically exactly in the same pod as your application container. So every container you run has a sidecar that is running this Envoy proxy. And this is how the magic happens. Now you can get all the authentication, all the encryption. You can get obviously tons of metrics. You can induce delays. And obviously, to manage all of these sidecars, there is a control plane that is, for example, could be Istio, or could be Linkerd, or could be any of those implementations. This is what you interface with as a user. And then there's a ton of observability tools for metrics, for tracing, for different purposes.
So from a packet flow perspective, then I could go into taking some steps back. I would let's go to the service level. I've got a service that goes to a virtual IP that then passes through eventually to a pod. It goes that NAT service and goes to a pod. When it hits the pod, if I'm running a service mesh, there's going to be a sidecar proxy that sits inside there that's going to be probably the container that's going to get that network stream and then pass it through to the app container that is then going to actually do the final processing. But it can manipulate that network stream in whatever way as you were describing, with delays, or it's doing encryption offload, or whatever else it might need to do, and then get passed from the app container in the pod back to the sidecar proxy in the pod and then back out again.
Yes. So basically, if you have two pods in the same, if you have two pods communicating east-west, every container will have to give it to its sidecar. And then the sidecar will have to give it to the other sidecar, which is, I mean, on the other pod. And that sidecar will have to give it to the pod.
Or pod to pod. Okay. So
exactly.
But this is also where the metrics are coming from, right? Because I've got that.
Exactly.
Okay. Yeah.
Exactly. Because you're getting all of these packets into those proxies, this is where you can do all of this magic in terms of visibility, in terms of other functions.
So going back to the control plane functionality, you mentioned Istio. So if I want to control all these sidecars at once, the control plane of Istio in this example, managing Envoy sidecar proxies, I am setting policies, saying what I need my sidecar proxies to do and so on from within Istio. And it's going to, I'm not programming sidecar proxies one by one. I'm defining them in Istio, and then as they're instantiated, as a pod comes up, it's going to get its marching orders from Istio.
Exactly. And what's interesting about all of these projects is they all have what is called CRDs, which is basically an extending Kubernetes to be able to have all of these additional definitions. So you basically interact all of this in Kubernetes, and there is the concept of what is called a virtual service. So we no longer use the service in Kubernetes. There is in Istio a higher construct called virtual service. Wow. And obviously, because you can think about it, like if you have a new deployment, right, and you want to test it. Today, a service in Kubernetes cannot give you 95% to the stable version and 5% to the new version. All of that in Istio becomes very easy. You say, I want to give my new deployment only 1% of traffic, or I want to give it to users that are coming with a certain header because you're testing, right? All of these capabilities are not there in Kubernetes. So this is why there are other constructs like a virtual service that go higher in the stack.
Now, I have heard that you don't install a service mesh unless you need a service mesh. And if you don't know if you need a service mesh, you don't. Does that sound about right to you?
If you really are operating at scale, you have a ton of apps, you need the visibility. I mean, then you might be looking at a service mesh. Apart from that, I mean, it's not an easy undertaking. And just to be fair also, Istio, for example, has, I believe they're launching a new project called Ambient. And the whole objective is to reduce the number of these sidecars. Because a sidecar per pod is a lot from a compute perspective. And obviously there are issues if you think about what happens if I want to upgrade my Istio or my Envoy proxy. What will happen to my application, right? These are all questions because you're living in the same pod. So they are moving to a per node proxy. Again, this is, I believe, either in beta or this is going to launch soon. But I think they realize that for many customers, they're still using it and they need it, but they're trying to simplify the process to get more customers on it.
Okay, so I guess that ties into sort of some of the downsides of service meshes is, just the resource consumption. If I've got one proxy per pod, that's a lot of potential work on a node, on a host.
Yes, obviously.
Yeah. Are there other downsides to the service mesh?
Again, what I mentioned is about having to deal with how does app upgrades versus sidecar upgrades. At the end of the day, this Envoy is a container. You need to upgrade, you need to maintain. These are mainly the common ones. And obviously there is a skill set, right? It's not like you can give it to a network engineer easily. It's generally, in my opinion, more app related. And there's a lot of, for example, for every request that comes, there has to be a request ID because this is the request that goes across all of the components, and this is how you can do a trace and see which component, for example, had the most latency. So I think it touches a bit of a different persona within the environment, in addition to the platform or network engineer.
Well, no, we've brought it up, service meshes, in this context of a network engineering discussion about Kubernetes. But it feels like service meshes don't really affect the network engineering team so much, or does it? I mean, how, if I'm on a network engineering team, do I need to care about the service mesh that a Kubernetes cluster that's running in my environment might be operating?
If you're operating the Kubernetes cluster underneath and you want to troubleshoot issues between communication, let's say between pod to pod that are going through these sidecars, then obviously this becomes part of your role because, if you want to troubleshoot it, then you need to understand, did the packet go from the container to the sidecar? Mm-hmm. And did the packet move? You have to go over the overall flow. But generally, if you're outside of this, then maybe you don't. But if you're managing Kubernetes, then I think it will come to you one way or the other.
What's interesting about this, a lot of the complex troubleshooting conversations I've been in over the years, even if it wasn't a network problem as such, the network is performing well, but being able to converse with the other engineers on the call as we're all banging our heads together trying to figure out where the issue really was super helpful. It's like knowing something about a web server, knowing something about certificate infrastructure, et cetera. Knowing how all those pieces work can help contribute to the conversation as opposed to being, service mesh thing, huh? Yeah, I got nothing. Not the network. It's good. Thumbs up and you walk away. That didn't help. But if you kind of understand what's going on, how it works and what the packet flow is, you can contribute to helping solve the problem. Even if it isn't, the network as such, but you have knowledge about what's really going on, that's incredibly useful.
Yeah, I fully agree. I think the context definitely helps one way or the other. I generally enjoyed it because I was interested to see how does the packet get to the sidecar and all that magic and what they do internally. But I think to your point, the more context you have about a problem, I think it becomes more solvable.
Now, is there a cloud version of a service mesh? Like when we're talking about Istio and Envoy and Linkerd and those, I kind of think of those, that's a cluster I'm running myself and I choose to add those services. But what if I'm on, what is AWS called? Is it EKS? Whatever their Kubernetes service is.
I think that's a very interesting one. AWS actually just launched what is called VPC Lattice. I really like it because the interesting part is, like everything AWS, they manage the proxies for you. You don't have to see proxies. You don't have to install sidecars. So what they do basically is they run a parallel network, that has these proxies, and they rely on DNS. So the other thing that I really like is when I mentioned the parallel network, it means your existing networking still works. If you are an AWS Transit Gateway or VPC peering, all of that still works, but they're linking you to a parallel network, and then DNS decides if you want to go the old way or the new way. Which is really, really smart. And there's no sidecars. There's nothing you have to manage. It does not have all the capabilities of like a service mesh per se, but I think the idea is pretty interesting.
I was going to say it feels very AWS of a way to do it.
Exactly.
Once again, they're doing it their own way, and it's very special, and it works magically with their stuff. So welcome to the lock-in.
Yeah, exactly.
Whew, okay, so that was a good, meaty conversation. Karim, thank you so much. If folks are interested, I mentioned you have a blog earlier. Where can they find your blog? And if you're anywhere else online, like a social media or LinkedIn?
Yeah, I'm definitely on LinkedIn, Karim El Jamali, and I blog also on jamali.hashnode.dev. I also have my blog post, thanks to the team, on their newsletter. Yeah, that's about it.
Okay, fantastic. Yeah, look for Karim on LinkedIn. We'll also have that link in the show notes, and his blog one more time, jamali.hashnode.dev. That link will also be in the show notes. And as Karim mentioned, we often feature his blog posts in the Human Infrastructure newsletter if you're interested in getting that. And if you've made it this far, congratulations. Thanks, Karim, for sharing your expertise with us. We're going to have all the links that we mentioned in the show notes, along with some other research. We'll also post a transcript if there's elements of this conversation that you'd like to review at your leisure, because we covered a lot. And as mentioned, Heavy Networking is just one show in our podcast network. There's Heavy Wireless with Keith Parsons, Packet Protector. It's our brand new security show with JJ Manella and me. And if our Kubernetes conversation has tickled your interest in cloudy topics, you can go find Day 2 Cloud with Ned Bellavance and Kyler Middleton, and Kubernetes Unpacked, where they discuss infrastructure operations and Kubernetes at length. I'm Drew Conry-Murray here with Ethan Banks. You can follow or connect with us on LinkedIn or chat with us on the Packet Pushers Slack group. That's packetpushers.net/community if you want to join that Slack. And if you have comments about this show, you can always send us some follow-up at packetpushers.net/FU. The FU always stands for follow-up, and we love getting those comments. Last but not least, remember that too much networking would never be enough.